Hello, I'm Jace Holmes, and this is my Physics 2211 Lab 4. In this video, I'll be talking about the lab in which we observed and measured motion of a swinging mass attached to an oscillating spring. We're going to analyze real video footage and predicted motion with a computational model, and as well as discuss what-if scenarios. The key idea in this lab is talking about conservation of energy, including the discussion of changing of potential energy and kinetic energy and how they relate to each other. Furthermore, by the end of this lab, we will discuss about how the change in total energy is zero and that the predicted and observed models are very similar. Like all labs we've had in the past, we're going to include Newton's second law, where the net force is equal to the change in momentum over change in time, as well as the velocity and position update formulas. In addition to this, because the lab is talking about the energy principle, we know that the energy of the system is equal to the work of surroundings plus heat, but with the work of surroundings and heat transfer being zero, we know that the change in energy of the system is the change in kinetic plus the change in potential, in which the change in kinetic is 1/2 mv squared, and the change in potential is broken up into a spring and gravitational change. And in this lab specifically, we know that the system includes the weight, earth, and the spring, with nothing being in the surroundings. Moving to the tracker data from the video, at the fixed attachment point at the top, that's where I set my origin, and where right before he actually picks up the weight and starts moving it to begin its oscillation, that's where I set the initial height at, which was 0.7 meters. We were told that the mass of the weight is 0.402 kilograms, and from tracker, I found from when the person in the video moved the block, its initial position was negative 0.102 meters in the x direction and negative 0.645 meters in the y direction. From my tracker data, I was able to find that the period of oscillation was about 1.52 seconds, and after some quick math, found that the spring constant was about 6.83. After finding these values and putting in the equations from the intro into the GlowScript code, we are able to run the program and get the following models. In the model shown on the right, it's actually seen that the computational and experimental models are very close and that they appear to be just shifted off from one another. Furthermore, on the graph on the left, you can see that the change in potential energy is perfectly matched with the change in kinetic energy, therefore giving that the orange line, the total change in energy, to be flat line, aka constant. Possible errors in this experiment is that the initial velocity during my tracking may not be absolutely zero. Because of the frame rate that the video was recorded at, I kind of just assumed that the moment I saw his hand let go of the mass, according to what I could see, the velocity was about zero. Additionally, we are assuming that there's no heat transfer nor deformation of the spring and no work due to any other forces being done on the system. And in the real world, especially the heat transfer and deformation, we know this to not be true. And lastly, is the energy principle satisfied? Like I just discussed, assuming that there's no deformation, no other work done, no heat transfer, according to this graph of the computational model, there was no change in energy. Therefore, the work of surroundings was equal to the work of the system, therefore satisfying the energy principle.